check on that part, okay? Do we know the angle of R2? Well, sure, it's the input angle, so we put I for input. R2 is always the input, so usually always the second overbar will always be over 2, okay? But maybe not. If they say 3 is the input for whatever reason, you'd put the input over 3, okay? But usually 2 is the input. Okay, now the question is, do we know the magnitude of R3, the length of it? Sure, we could measure it. It doesn't change as theta 2 changes. This is a checkbox. We know it. Okay, so here's the first overbar corresponds to the vector length, second overbar corresponds to the vector angle. You see, okay. So let's do the vector angle. Do we know theta 3? No, we don't. You know, so theta 3, you couldn't just, like as theta 2 changes, theta 3 obviously changes. So it's obviously a function of theta 2, and so you don't know that, okay? That's the unknown you're trying to solve, okay? And that's not given. I could hand you the mechanism. Depending on what position it's in, it's going to change, okay? So you don't know that. Okay, R4, the magnitude we know, the length we know, check. But the angle we don't know. That's another question mark that we have to put, okay? Now, R1, do we know the magnitude of R1? Yeah, we could measure the difference between those pins, and it doesn't change as theta 2 changes, so we know that. And then, does the angle of R1 change? Do we know that? No. Well, yes, we do. We could measure it. It doesn't change. It's actually 0 radians, because it's just a horizontal line pointing to the right, okay? So we do know that, and it is 0, okay, in this case. So once we do this bookkeeping trick where we use some of these symbols in the magnitude and the angle position of all these things, we can quickly see what we know and what we don't know, okay? And for any vector loop that you use in this course, you should never have more than 2 question marks. Do you know why? Well, because there's 2 equations in this vector equation, right? The x component and the y component. And so if you ever have 2 equations, you need 2 unknowns, no more than 2 unknowns to solve those. Okay, if you have 2 equations and 2 unknowns, you can solve it. Okay, so that's why when you do 2-dimensional vector loops, you always want 2 unknowns. Okay, now if this was a 3-dimensional spatial mechanism, and your vectors, you were considering the 3 components, x, y, and z, then this vector equation would be 3 equations for the x, y, and z components, and you would want to find 3 question marks, okay? Because now you have 3 equations, 3 unknowns, you can solve it. If you ever have more question marks, though, than equations, you're in trouble and you're not going to be able to solve it, and you know you've drawn a bad vector loop, okay? So I'm going to do an example of this, okay? So, okay, so here's our slider crank mechanism here, okay? And let's try drawing a vector loop, okay? You might, and by the way, there's not just one right vector loop answer, okay? There's actually, there could be many right answers. There may be some examples where there's one right answer, but there's certainly plenty of wrong ways you can do it, okay? So let's just try a way here first because we've never done this. So you might think, okay, well, I mean, it's obvious to draw the vector from, you know, to connect, always connect the pins. That's always going to be what you want to do first, okay? So let's connect these 2 pins, and this all obviously corresponds to link 2, so we'll call it R2, and make sure you label it with the right number that corresponds to, you know, the link that the vector is describing, okay? So that's definitely R2. You have to name it that. If you named it anything else, you'd get a wrong answer on your exam, okay? And then R3 is another easy one from this pin to that one. Just draw it, and of course label it R3 because it will tell you everything you need to know about link 3. And remember, we could have put the head of this one down here. We could have put the tail there. We could have put, you know, the direction of the arrow doesn't matter at all. You just arbitrarily pick it. Okay, so fine. Now you could close the loop by doing a vector from there to there. That's what a lot of people would likely do for their first try. And so, you know, and this one, we name it, since it doesn't really, well, it would kind of describe the sliding of 4, so we named it 4 here, fine. Okay, but now we've closed the loop, and we think we're happy. Okay, so we've got, we've drawn the vectors, we've arbitrarily put their heads and tails on them however we want, the vector loop is closed, and we can start in some weird location, start wherever you want, you can start anywhere you want, walk around in any direction. We're going to start this way, and walk this way. So we're going to start here at the base here, and we're going to walk clockwise, just arbitrarily, okay? And so we walk, since this is tail to head, we make this plus. Since this is head to tail, we make this negative. Since this is head to tail, going back, we make this negative. Okay, and you could see we could go the other way, or we could start there and walk this way. And no matter what as long as we follow that convention with the signs, this will always equal 0. And you should, again, prove yourself to that. Okay. Okay, so good. So you're following the steps. You've got a vector loop drawn. You've got a vector loop equation drawn. This is a true equation. It's always going to equal 0. But the question is, you need to do that bookkeeping step before you write it in component form to make sure you can solve the equation you just found. Okay, so let's do this thing. Let's ask ourselves the question: do we know the magnitude of R2? Yes, we do. You could measure it. I could give it to you. It doesn't change as theta 2 changes. Okay, so we know that. Okay, and by the way, theta 2 would be from this horizontal line up to there. Okay, okay. So, and do we know that theta 2? Well, that's the input. That's what the motor is. So we're going to do I. Okay, that's going to be I there, the input. Okay, and then R3. Okay, do we know the magnitude of R3? Well, sure, we could measure it. It doesn't change as theta 2 changes. It's a known, so we put a check there. Do we know theta 3? And first of all, theta 3 would be defined, since here's the tail that we drew, would do a horizontal line, and theta 3 would be a green line that would go that way. Okay, so do we know that? Well, another way to ask is, does it change as theta 2 changes? If I give it different positions, would the position or orientation of R3 move? And the answer is yes. So we definitely do not know that. That would be a question mark. Okay. R4, do we know the magnitude of this? Can we just measure it? Does it change? Like, yeah, no, because, well, yes, it does change. We couldn't measure it because as theta 2 changes, the length of this is going to stretch or contract. If it moves back, it'll contract. If it moves this way, it'll stretch as we change theta 2. So we don't know the magnitude of R4. Do we know its angle? Will the angle change as theta 2 changes? If I move this down or move it up, will the angle of theta, will the angle of this guy change? And by the way, that angle, since the tail is here, we draw the horizontal line here, and it would go all the way around to define theta 4, okay? And that theta 4 that would go from this horizontal line all the way around would indeed change as theta 2 changes. So, we have another question mark. So already, even though we've done the loop closure, equation correctly, and we've written a correct vector loop, we are running into a problem here, because you're going to see, you see that there's 2 equations here, but 3 unknowns. So it can't be solved. So you did everything correct, but you set something up that can't be solved. It's impossible to solve, so it's no good. If you run into that, your first attempt is a bad attempt. Okay? So you got to start over. We have to draw a different vector loop now to solve this. Okay, so let's go over to attempt 2. Okay, let's try this. So too many question marks here. Okay, so let's draw this. So R2, let's do the same R2, let's do the same R3, because you always connect pins, especially if they're on the same link. That's always going to be what you want to do, and it's going to be correct. Okay, but this is a little tricky. Let's now draw R4 there, going this direction, because what we care about is the translation in this direction. Then let's draw R1 there. Okay, so now we label this 2 because this one clearly captures the rotation of 2. We label this 3 because it clearly captures the rotation of 3. We did label this 4 because it clearly captures the translation of 4. So it's everything we care about 4, which is its translation, we are being captured by this vector, which is why you need to label this 4. And then we could have, I guess this captures the movement or the orientation of 1, and so we name it 1 because it's ground, it's not going to move. Okay? So we had a vector for every link, which isn't, don't think you should have a vector for every link. There's vector loops where you have many more vectors than there are links, okay? And they're correct and they work, okay? So don't think that's a rule. In this case, we happen to have as many vectors as there are links, and this one defines R1, okay? Okay, so let's try that vector loop. And by the way, if you're like, well, how did you know to draw it that way? I'm going to give you rules and tricks so you can know how to draw it that way, okay? All right, so let's do this here. We drew our vectors. We arbitrarily put the heads and tails wherever we want. We can start wherever we want, walk in any direction. Looks like, again, we coincidentally start at the origin. We're just going to walk clockwise. I don't know why we keep doing this. I should have done some examples where we start, say, here and walk counterclockwise. It's all the same, okay? But since we start here and walk clockwise, we do plus, minus, minus, minus. Okay, just because of how we drew the arrows. Okay, and so you see plus, minus, minus, minus. Okay, and that will equal 0. Okay, so now before you do anything else, let's do our bookkeeping trick here. Okay, do we know the magnitude of R2? Well, sure. Do we know its angle? Yes, I give it to you. It's the input, I. Okay, do we know the magnitude of R3? Yes, it won't change as theta 2 changes. So yes, we know that. Okay, do we know the angle of theta 3? That's going to be horizontal line there to there. Does that change as theta 2 changes? Yes, it does. We don't know. That's one of our question marks that we don't know. And that's something we would probably care about finding. Okay. R4, do we know the magnitude of R4? The length of this? No, we don't. As theta 2 changes, this guy's going to stretch or compress. Okay, and so we don't know the magnitude. That's another question mark. We don't know that. Do we know its angle? Sure, it's always going to be 0, right? Here's its tail. We draw a horizontal line, do a thing going up to it, which is nothing because it's horizontal, so it's 0. So we know what that is, and we know it's 0 because it's horizontal. Okay, do we know the magnitude of R1? Sure, we can measure it. In fact, it's already given to us. It's h. We know that. Okay, and it's not going to change. No matter how much theta 2 changes, h stays the same. So we know that. Check. Okay, do we know its angle? Yes, we do. That angle is never going to change as this moves, as theta 2 moves. And its angle is going to be, find its tail, do the horizontal, and do a green line all the way around there. So it's 3 pi divided by 2. And always use radians, or you'll get really messed up. So it's important. So you do know this. Check, and it's 3 pi divided by 2. That's that's the angle of R1, and it's never going to change. So that's why you know it. Okay? So aha, we now have a new vector loop equation that is true and works, and we follow the convention. And again, it's 2 equations, and fortunately just 2 unknowns, so it can be solved. And what you would do then is write this equation in component form, put all the x components on the top and give them all the signs in our convention. Put all the y components on the bottom and use all the signs from the convention. And then define define the angles as I told you to from the tail. And you would find, plugging in what we know, right, which is that r theta 4 is 0, okay, and therefore cosine 0 is 1, okay. And theta 1 is 3 pi over 2, which means cosine of 3 pi over 2 is 0. And again, this guy, that guy is 0. And so this is 0. And this is, 3 pi over 2. And so that's negative 1. So if you rewrite that equation up here, you get this. And sure enough, now you have 2 equations and 2 unknowns. There's your theta 3, and there's your R4. So those ones that are circled there are your unknowns. And you could solve it because you've got 2 equations, 2 unknowns, the rest you solve it. And now you've done position analysis for a given theta 2. You can now solve for theta 3 and R4. And chances are it's the R4 you care about, the magnitude of R4, the length of this for a slider crank. You probably don't care about theta 3, but you need to solve it to solve R4, so you solve it. And maybe there's an example where you'd want to know the orientation of theta 3. Okay, so now let's look at this example. Okay, we're going to do a bunch of examples here because this is, exactly what you want to be able to, this is the most important concept in the class. Like pretty much every exam, there's going to be a mechanism, and you'll have to start by drawing the vector loops, and you're going to have to do a position analysis first, and then velocity analysis, then acceleration analysis. And so if you don't get this right, all the other parts of the question you're going to get wrong. And you can see everything builds off of this. So super important you understand this, okay? So let's look at this mechanism. In this mechanism, you've got this big circular kind of cam thing. It's not its center is here, this cross thing, but it's actually pinned to rotate around an off-axis thing that's some distance d away. Okay, this is link 2. It's labeled 2. And this is link 3. And of course, these guys are stuck to ground. So it's a 3-link mechanism. Again, from last lecture, or topic 1, it's not a linkage because this is a higher pair. This is a higher pair. And it does allow rolling and sliding. Okay, so It's a 2-degree of freedom joint, not because it's a higher pair, but because it's just 2 degrees of freedom. Whether it's a higher pair or in degrees of freedom, remember, are the unrelated principles. Higher pair is whether things touch at a point or a line, as opposed to a lower pair that touches at a surface area. Okay, so it's just a little review. Okay, but let's do a vector loop of this mechanism. Again, not linkage. Okay, of this mechanism, and see if we can do position analysis. Okay. All right. Well, okay. Someone might say, let's try this. You might say, okay, let's go from this. Let's just connect all the joints, right? So we've got a pin joint. That's usually a hot spot where you want to put a vector. Okay, but let's go to this joint where that touches, that 2-degree of freedom joint that rolls and slides, which is a good, it's a good thought too. Okay, and then we'll go from that joint to this pin joint, which, by the way, they really should have drawn this better. This should be slightly off axis so that this red line is parallel to this bottom curve. This wasn't drawn carefully, so that black dot should be right there on the edge. Okay, and so you could try that, and that's good. And then you probably connect the 2 pins. Connecting the 2 pins is usually the most obvious. Okay, and of course, you'd think, okay, well, this captures link 2, so we call it R2. This captures link 3, so we call it link 3. And this captures link 1 and its behavior, which is it doesn't move, and that's R1. Okay, so that looks like a reasonable vector loop. Again, we arbitrarily put the head and the tail in whatever direction we want. We're going to start at some point and walk around either clockwise or counterclockwise. It looks like in this case, we start here and walk this way around. So it's tail to head is plus, head to tail is negative, tail to head is plus. So plus, negative, plus. Okay? And that equals 0. That's a true statement, but is it going to work? Okay, well, let's ask ourselves, do we know the magnitude of R2? Boy, no we don't, because as theta 2 changes, remember, if this is R2, you do a dotted horizontal line and define theta 2 as that. As that changes, you can see this magnitude will actually change. And in fact, in the short term, it's going to get longer and longer because this is rotating off axis. The distance from there to there is going to be a lot shorter than the distance from there to there when that's finally pushing that. So you can see we don't know this. It's going to get longer. It's going to change as theta 2 changes. The input we know, that's theta 2, so we make that I. Okay. Okay, R3, do we know the magnitude of that? Well, that one's going to change too as this rolls. That's going to lengthen and shorten, so we don't know that as theta 2 changes. And also the angle we don't know. Or the angle of theta 3 is the horizontal line here, and theta 3 is this angle. Okay, that will also change because it's rotating off axis. It's going to push it up, and this will lift up. So that's another question mark. Already we have 3 question marks, so we're in trouble. R1, we could just analyze this real quick. We do know the magnitude. It's not going to change. It's just 2 points on the fixed link. And we do know the angle. It's 0, right? Horizontal down here, 0. Okay? So, but we're in trouble. We've got 2 equations, 3 unknowns. No good. Okay? So let's try and attempt 2. Usually... So you always point your vectors to the pins is usually a good idea. But also if you have centers of circles, you could always try pointing to those. That's always a good idea. And I'll show you how it works in this one. Okay, so let's try pointing from this pin to the center here. Now those are 2 points on link 2, and they're going to move with link 2. So we better name that R2. That's the new R2, the new vector that captures the rotation, the movement of 2, okay? Do you see how the center of the circle and that point, those both move with 2? So that captures 2. And then let's point a new vector from the center of the circle to there, okay? And one thing to notice, the reason that's smart to do, is no matter how this rotates around here, that vector that points from the center of the circle to the point where it touches there is, first of all, it's always going to be the radius, so we're always not going to know the length, but it's also always going to be perpendicular, right? Anytime you take a circle and push it up against a bar, no matter how much you rotate and push on it, if you draw a vector from the center of the circle to where it touches, it's always going to be perpendicular to this, and it's always going to be the length radius r, right? So that's a good one to pick. And notice we called it R4. right? Why do we call it R4? There's no 4 link. So how could you say that captures the location 4? Well, you're right. There's only 3 links. There's the ground, link 1. There's the input, link 2. And there's the output, link 3. Okay? And so this doesn't capture the motion of any of them. So as long as you don't name it R1, R2, and R3, you can name it whatever you want. The next obvious name to give it is R4, even though there's not a 4th link. So you could do that, but you could call it, R2D2 for all you want. You can call it anything. RL, R nothing, R10. You can name it anything you want, and you wouldn't get a point off on an exam. So it's really important you call this one R2 because it truly captures the motion of 2. And it's really important you call this one R3 because it truly captures the motion of 3. And it's really important you call this one R1 because it truly captures the motion or lack of motion because it's a ground of R1. But this one, you can name anything you want. In this case, we named it 4 because that's the most obvious name after 3. Okay? So we're going to try this. It's very similar to this, but the only difference was we did those 2. Okay, let's try this. Again, we could have put the arrowheads any direction we wanted. We're going to start anywhere and walk around anywhere. Let's see where we start. Okay, in this case, we started here again, and we're walking this way. So we do plus, plus, minus, plus. Plus, plus, minus, plus. Just because of how we drew the arrows. If we drew them differently, signs would be different, but it would still be correct, and you'd still get same credit on an exam. Okay, because it's correct. All right. Okay, so that's good. Now let's try this, though. Let's do the bookkeeping before we move on. We've drawn the vector loop. We've labeled them appropriately according to what bodies it captures the motion of. And now we're going to go through here. So R2, the magnitude of that, do we know? Sure we know it. It's the distance between this pin and the center of the circle. That's something we can measure. That's something that doesn't change as theta 2 changes. Okay? It's just those are 2 points on a fixed thing. We know that. All right. Do we know its input? Yeah, sorry. Do we know its angle? Yes, it's the input. Okay. So since here's the tail, you draw a horizontal line and you draw the angle up there, which you can see there is theta 2. Okay, and that's the input. Okay, so that's I. Okay, R4. Aha. Do we know the magnitude of R4? Well, yeah, it's always going to be from the center of the circle to where it touches this bar. Okay, and so the magnitude, that's always going to be R, or the radius of the circle. So we know that. Magnitude is R, the radius of the circle. So that's a big check. We know that. Now, do we know its input angle? So remember, if this is the tail, we're going to draw a horizontal line there, and theta 4 would be this angle right there, from a horizontal to there. Do we know that? Well, no, and that is going to change as theta 2 changes. Okay, you can imagine as theta 2 changes, that's going to change, but it's going to be a function of theta 3. So remember, there's theta 3. And again, I wish that pin was moved a little over so this red line was parallel to this line. That's what it should be. Theta 3 is from the horizontal there to there. And so you can see it's actually constrained C by this equation. Okay? So here is the first time we're using the C, the constraint thing. Okay? So remember, here's theta 3. Okay? Here's theta 4. And it's constrained because we know this will always be 90 degrees or pi over 2 radians. Okay? No matter what. If the circle touches that, it's always pi over 2. So you can know if this is theta 3, so from the horizontal up to there is theta 3, plus pi over 2, this is always going to be a 90 degree angle, that will equal theta 4. So this is a new equation we're introducing. You could either think of it as, we don't know this, but we're going to introduce a third new equation, or it's just constrained, and here is the equation. Okay? So this is just how this works. You know, if you know it, you do a check. If it's an input, you put an I. If it's unknown and it's an independent unknown, you put a question mark. But if it's a dependent unknown and it's linked to one of the other unknowns, then you put a C and you introduce the new equation that relates them. Okay? So R3, let's get to that one quickly. R3, we don't know the length of this. This is going to shorten or lengthen as this rotates off axis. So that's a question mark. We don't know that. Okay, and we don't know the angle either. Theta 3 will certainly change as theta 2 changes. As this moves, this will get bigger or smaller. Okay? So that's a question mark. But remember, that is a creates a function with theta 4, which is why that's C. Okay? Okay, so R1 is magnitude. You know that. This is not going to change. It's captured by R1. And you know the angle, check, which is 0 in this case. Okay, so great. So we have two equations and two unknowns. Or you could think of it, we have the two equations here with plus a third equation and three unknowns. Either way, you have as many equations as unknowns. And you can solve it. Okay, and so you could go on. You could write this in component form. You could simplify it and then identify your two unknowns and solve for them. And let's do it. That's what is next. Here's the components of all of these vectors with the signs. Okay. We know theta 1 is 0, so this is 1. We know this is 0 because sine of right? Sine of 0 is 0 there. And so we simplify this equation to this. And here for theta 4, we plug in this. Theta 3, notice we put theta 4, we plug this in, and we got that. So here's the simplified equations. And you see here's one of the unknowns, and here's the second unknown. Okay? So we have two equations with all the knowns in there, and two unknowns. Two equations, two unknowns, and we could solve it. And I'm guessing for this, the output, the really unknown that you care about is theta 3. R3, the length of that, probably you're not going to use for the mechanism. You probably don't care, other than the fact you have to solve it to find theta 3. But theta 3 is probably the output variable. You put the motor on this one, and you're probably going to care about how this one rotates. Okay? All right. Okay, so this one is an inverted slider crank example. It's actually very similar to the last one. You got a slot, prism joint sliding in this slot here attached to these things. Let's do the vector loop for this is actually pretty easy. You connect the pins there, those are the two easiest. You call this R1 because it captures 1. You call this R2 because it captures 2. Okay, that's R4 there. Let's say, yeah, that's R4 because that will capture the rotations of 4. Okay, the length 4. And then here's, from the center here to that point, that's R3. That'll capture the rotations of 3. Okay? All right. So, okay, great. And notice the angle between here, again, is always going to be pi over 2 or 90 degrees. Okay? All right. And again, the where we put the heads or tails doesn't matter. We're going to march around in some way. Okay, looks like we finally didn't start at the origin for this example. We start over here. The origin's here, but we're going to start here, and we're going to walk this way. So plus, 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 minus, plus, 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 minus. Okay, and then let's do the equation thing here, the bookkeeping. Do we know the magnitude? Yes, we do. Do we know the angle? Yes, we do. It is 0. Okay. Do we know the magnitude of this? Yes, we do. It's a fixed length. It's not going to change. Do we know its angle? Yes, it's the input. The motor is apparently attached here because it's 2 driving 2. And theta 2 you can see is drawn there. Do we know R4? Yes, it's a magnitude. Okay. Do we know its angle? Not so much, but it is constrained by this equation. So you put C, and it's the exact same equation before. Remember, this is theta 3 right there. If you draw, theta 4 is going to be from the horizontal here up to there. So it'll be theta 3 plus pi over 2, which is right here, equals theta 4. So again, it's constrained. Same thing as the last example. And then we don't know the magnitude of R3 because that slider is going to slide and change length. And we don't know that. And then we don't know the angle of R3 that captures the orientation of 3. So we don't know that. So again, we have, you can either think of 2 equations and 2 unknowns, or 3 equations, 2 in there and 1 there, and 3 unknowns. Either way, you can solve it. Okay? And we have here, that's the equation. You just write it, the component form out. You simplify it. Let's plug this into theta 4. And simplify, we know theta 1 is 0. So, simplify that. Plug this guy in there, and you get this. So here's the component form of the vector. loop equation, all simplified with things you know, and then you identify the things you don't know, theta 3, which is probably what we care about, and then R3. Okay? So we're going to solve both.